Hi. Hi. My name is Kenta Murata. I have three happy things in this RubyConf. The first happy is that this is my first attending RubyConf. Thank you very much. Thank you very much. The second happy is that this is my first leaving from Japan. The last thing is I got new Kindle today. So I'm very happy. Okay, I start my presentation. I'd like to talk about the decimal fraction in Ruby script. I begin this talk with my introduction. I am a C Ruby committer interested in numeric system. I maintain big decimal and OS 10 support. I am 10th of committer ranking as of today. I'm here. And I'm from Sapporo, Japan. In Sapporo, there is a community named Ruby Sapporo. Ruby Sapporo is a community for studying Ruby and other technical interests. My hometown, Sapporo, is very beautiful and very tasty city in Japan. Unfortunately, the Ruby Kaigi is not held in the next year. But fortunately, regional Ruby Kaigi is continued in the next year. I have good information for you. The fourth Sapporo Ruby Kaigi will be held in the next summer. The official information will be published soon. I will forward the announcement to Ruby Talk and Ruby Core. Please wait and please come to Sapporo. Next, I thank two friends of mine. One is Tatsuro Ujihisa in Hootsuite Media Inc. He gives me the cool talk title, Float is Legacy. I love this title. It is very short, but well describes my opinion. Another is Yoshimasa Niwa in Twitter Inc. He often supports me about English language. Thank you very much. Now let's start my talk. Let's begin the summary of this talk. I want to describe these topics. The first is about the system of floating point numbers. I will explain that the use of float class requires us advanced knowledge about floating point numbers. Next, I will mention that most Rubyists don't need a float class, and rational class is enough for them. Finally, I will show you that literal of decimal fraction interpreted as rational makes us more happy. We usually use float values in everyday scripting in Ruby because they are generated from literals of decimal fraction. But I believe we don't understand the float class well. So first of all, let's begin with a short review for remembering float class of Ruby. Do you know what is the float class? It is a wrapper for C double type. It is boxing a value of double, so it requires object allocation to generate a new float object. Since float is C double, we have to know C double to understand what is float class. C double is a type of floating point number with double precision. The standard C doesn't specify what is double precision. Sorry. Most current platform employs IEEE 754 floating point number system. On these platforms, C double is IEEE 754 binary 64. There are platforms employing other specifications, such as IBM System 360. Be careful, C Ruby and JIS Ruby don't require IEEE 754. In other words, the standard Ruby allows arbitrary floating point number systems. Next, I want to explain how floating point numbers are difficult and troublesome. I believe we learned this number format in physics or chemical classes. This scientific number notation is the origin of floating point number notation. The scientific number notation consists of three parts. They are sign, fraction, and exponent parts. Floating point number notation also consists of these parts. And the limitation of these parts are represented in these equations. So floating point numbers can be identified by triplets, which consist of sign S, exponent E, and fraction F. These triplets represent approximation of real numbers, and floating point number types can be described by 5 parameters. The first parameter, B, is the base number of the exponent part. The next, N, is the number of digits in the fraction part. Q is the bias for the exponent part, and E max and E min specify the limit of the exponent part. Using these parameters, a floating point number is denoted by this equation. For example, IEEE 754 binary 64 is described this parameter set, and the maximum and minimum non-zero positive numbers are in the right side on the slide. The values on the right side can be calculated from parameters on the left side using this equation. The next example, IEEE 754 decimal 64 is represented by these parameters as well as binary 64. And the last example is double precision system of IBM System 360. There are several real systems of floating point numbers. So I want to recall one thing, that is floating point number represent approximation of real numbers. Do you understand how it is? I try to describe that by illustration. Suppose a number line. Every integer is mapped from a point on the number line, and every rational is also mapped to a point on the number line. But every floating point number is mapped from every element in an open range on the number line. The top mappings are one-to-one mappings, but the bottom mappings are not. We must use the representative number instead of real numbers in a region on the number line. So we should think there are no numbers represented exactly. We should think floating point numbers always include errors. And we should think the magnitude of error depends on B, N, and E. Why floating point numbers include errors? These errors are avoidable rounding errors from using place value notation with finite digits. In place value notation with finite digits, very few values can be specified exactly. We shouldn't expect that any given value is exact. Now, I want to consider a question. how many decimal fractions can be exactly represented in the form of binary fraction? Let me show you deriving the answer. Decimal fractions can be represented as a fraction whose denominator is the power of 10. And binary fractions is similar to the decimal ones, except that the denominator is the power of 2. So this is generalized for arbitrary number of digits. We have to focus these denominators. Thus, decimal fractions can be exactly represented as binary fractions only if its denominator is the power of 2. In other words, if the numerator of decimal fraction is divisible by the multiple of 5 raised by m, the decimal fraction can be represented as a binary fraction exactly. Now, we get the answer of the question of how many decimal fractions can be exactly represented as a binary fraction. This chart illustrates the answer. The blue line represents the ratio of exact numbers, and the pink line represents the ratio of inexact numbers. Look at this yellow dash line. This dash shows the position of IEEE 754 binary 64 system. In this system, as you can see, almost all numbers are inexact. Now let's summarize about decimal fractions in binary form. First, n-digit decimal notation is exactly represented in binary notation only if its numerator divisible by 5 raised by n. Next, the ratio of n-digit decimal fractions exactly represented as a binary fraction is 1 over 5 raised by n. Finally, in IEEE 754 binary 64 system, almost all numbers are inexact. As floating point numbers include errors, floating point arithmetics also works with errors. I don't mention it in this talk. Please read good papers such as What Every Computer Scientist Should Know About Floating Point Arithmetic. So we have reviewed and studied the issues about floating point number system so far. Now we have enough knowledge for considering decimal fractions of Ruby. I consider that decimal fraction of Ruby have some problems. Ruby interprets literals of decimal fraction as float instances. Thus, the following 3 numbers are float, so they have errors. I think it is no problem that the last number has error, but I think it is problem that the first 2 numbers have errors, because I believe most people expect the first 2 numbers are exact number, don't have any errors. There are many issues about float reported to readmine. I think these issues are caused by floating point number errors. Do you know these issues? I picked up one issue recently reported. This is a bug number 4576 about range step. The title is range step miss the last value if end exclusive and has a float number. This issue is completely caused by that floating point numbers include errors. I'd like to show you this issue in demonstration. I used in this demonstration this version of Ruby. It is trunk. So the first example is about a range including the end 1.0 to 12.7 dot step with 1.3 dot 2a. So as you can see, the last value in the result array is larger than the end of the range. The next example is about a range excluding the end 1.0 to 128.4 dot step with 18.2 dot 2a. Yeah. As you can see, some elements including errors. And the result array have sorry. sorry. I mistake. So, and as you can see, the last value of the result array is too near the end of the range. Using rational, more exact result So, in the so as you can see, the size of result array is different. In using float, the last value is 128.4 is not including range, but using float, this is including in the result array. Back to my presentation. So in this demonstration, we can see the two problems. In the first case, the last value of the array is not equal to the end of the range. In the second case, the array size is one larger than the right size. For resolve this problem, I propose two ideas. The first idea is rational with decimal notation. It introduces one flag into a rational object. This flag represents a rational seems which fraction or decimal. If the flag is true, a rational is converted decimal string by 2s. Next, the second idea is literal for rational with decimal notation. It is a simple change for the parser. After the change is applied, the parser interprets literal of decimal fraction without exponent as rational with decimal notation, since literal of decimal fraction with exponent stays on float. We still have float literal. I've already implemented these ideas. Let me show you them in the demonstration. I use same expressions used by the previous demonstration for comparison each of these. I use the same version of the previous demonstration. The first example is 1.0 to 12.7 dot step with 1.3 dot 2a. As you can see, all items in the result array are decimal fraction, and the last value is equal to the end of the range. These values are rational. Look at this. These are rational. The second example is 1.0 to 128.4 dot step with 18.2 dot 2a. As you can see, the result is correct, not including errors. So as you can see, two results are right. I think it is better than the current implementation. But to demonstration, don't illustrate the calculation speed. You may mind that rational is very slower than float. So I compare the calculation speed of float, rational, and CW using a simple benchmark. I used my MacBook Pro for benchmarking. The spec of my Mac is here. I uploaded benchmarking code to GIST. You can access these GISTs in these pages. This chart illustrates the result of benchmarking. The vertical scale is the spending time of calculation. I do 3 benchmarking about addition, subtraction, and multiplication. Each operation is performed 1 million times. Since the result of CW is difficult to see, I prepared another view with magnifying the vertical scale. The benchmark tells us 3 facts. The first, rational is 2 to 5 times slower than float. The second, float is 2-digit order slower than CW. Finally, CW is amazingly fast. If flow num is implemented into Ruby VM, the result of float becomes more faster, I think. As I confirmed to Koichi Sasada, flow num is twice as fast as the current float. So flow num is as slow as rational than CW. Comparing CW, I think float is as slow as rational. So if you said rational is slow, float isn't as fast as you expect. So I think we can use rational instead of float for everyday scripting. Most applications require fast floating point number operations. Do not treat individual floating point number. These applications need to treat values in array. So if you need faster computation, you must use n array or other solutions. Which would be better, rational or float? The answer for this question depends on the situation of coding. Exact computation is required by domains such as finance. In contrast, float is required by scientific computation. But these cases are not common in the use of Ruby. Most situations of Ruby scripting don't depend on whether rational or float. So while Ruby is human-oriented, the number system should be human-oriented too. Now I conclude my talk. The first float is difficult, troublesome, and not human-oriented. In contrast, rational is easy to understand and human-oriented. Finally, it makes us more happy that Ruby interprets literal of decimal fraction as rational. So I want to assert float is legacy. That's all. Thank you very much for your kind attention.